Hey guys, today we're talking about using graphs and tables of functions. Being able to read a graph or being able to read a table is absolutely essential to our study of algebra. In fact, it's a great life skill to have, being able to gather information from a graph or a table. So today we're going to start in by just following a few examples and see what we can learn about reading from tables and graphs of functions. In example 1, we see that we have Maria who's traveling a distance on a 7-hour trip. She stopped at a historical museum for some time, drove a little bit further, had dinner, and then she returned home. So let's take a look here and see what we can interpret from this graph. It says which variable of this function is a function of the other. Which one's the independent and which one's the dependent? Well, remember our independent is our x. Along our x-axis here is time. So we're going to say that time is our x variable here. It's our independent variable. All right, therefore, along our y-axis is our distance, and therefore distance is our y variable. It's our dependent. So we would say that our distance is dependent on time. Okay, now let's state the domain and the range. Again, looking at our graph, we know that the x-axis is our domain. So our domain here is time. And if we want to state that domain, we'll use our set builder notation, which says t such that t is less than or equal to 0, or sorry, greater than or equal to 0, but less than or equal to 7. In other words, the time that she traveled goes from 0 to 7. All right, now remember our range is our y variable, our y-axis. So if we're looking for our range, we're looking for the range in the distance. So let's again use set builder notation here, d such that d is greater than or equal to 0, but less than or equal to 100. So if we were to cast a shadow against that y-axis, we'd see that the top of that shadow is here at 100, it goes all the way down to 0. So we'll say that is our range for that function. Now it says estimate Maria's distance from home after 3.5 hours. So using 3.5 as our value for x, we're going to come along the x-axis 3.5, and we're going to go up to that function to see the distance that she is away from home. It looks like it's somewhere between 75 and 100, so we'll just estimate it at about 87 miles. Part D asks us to estimate how much time it took Maria to be first 100 miles away from home. So it looks like 100 miles appears first here at 4 hours. All right, next it says, what is the significance of the left horizontal line segment? Estimate its endpoint. So I'm just going to highlight that here in a different color. Let's use yellow. That horizontal line segment that stretches from, it looks like about 1.575 to 375. So we'll write that down as, let's change colors back here. I'll say it's 1.5 comma 75 is one endpoint, and the other endpoint is 3 comma 75. So between 1.5 hours and 3 hours, she didn't move any distance away from home. So this is the significance of this little horizontal line here, is the time that she spent at the museum. In example number 2, we were given some information about Robert Waldo, who is the tallest person in medical history. So what we see is this table here shows us 2 rows. We have the row of his ages, and then the second row is the height in meters at those particular ages. So let's see if we can glean some information and be able to answer some questions regarding Robert Waldo, who's just a little bit shorter than me, Mr. D. I'm pretty sure that I'm the second tallest person in this picture. All right, now what is the domain defined by this table? So this is an example of a discrete domain. Discrete simply means it's not continuous. They're just specific points. So the domain here can be listed actually just using these points: 8, 10, 16, 18, and 22. Remember, the domain represents our independent variable. It is the x variable. Now it says, what is the range? The range is the height, because the height depends on the age of the person. So our range here, again, we're just going to list those individual numbers. We have 1.9, 2, 2.4, 2.5, and 2.7. So there's our range. Now it asks us to find f of 16 and then asks us, what does that represent? So f of 16 means that 16 is our input. So we're looking for our independent value, that is 16. Here it is. And what is its result? It is 2.4. So f of 16 is equal to 2.4, and this represents his height at age 16. All right, next it asks us for what the value, or sorry, for what value of a does f of a equal 2.7? In other words, f of some age is equal to 2.7 meters. How old or what age was he? 0.7 meters. So we're going to go back up to our table here, and we see when he's 2.7 meters, he was 22 years old. So we say for a value of when a is equal to 22. All right, in our next example, again, we're given another table and we're asked to glean some information from it. It says, what is the domain and the range? So again, we have our domain listed here as our x value and our range listed here as our y value, our inputs and our outputs. So to list our domain, we have some discrete values. We're just simply going to list those values here. All right, now to list the range, I see that they're all the same values here. So I don't need to list repeat values. So in fact, I'm just going to keep it at -3, and that is a sufficient enough job to list the range of that function. Next here in problem form 5, we see that w of x gives us the weight at age x of a baby during the first 3 months of life. So we look over here at our chart, and it looks like a baby starts off right around 130 ounces, dips down to right below 120 ounces, and then continues to grow. It says give the range of that function. Now remember, range is found along your y-axis, so let's cast a shadow along that y-axis. Looks like it's just over 180 all the way down to just below 120. So we'll use set builder notation, and we'll say our range are the set of y values such that y is greater than or equal to 118, but less than or equal to 182. Now we want to estimate w of 50. So in other words, at 50 days, what can we expect in terms of the weight of a baby? So here's 50 on the x-axis. I'm going to come up to the function. There it is, and I'm going to trace it back to the y-axis. I see that's right over 160. So I'm going to say that the weight at 50 days is approximately equal to 162 ounces.